So we're talking more about forecasting today. We're going to go through some of what we're calling advanced methods, although, I will tell you that just because they are more complicated in terms of the calculation does not necessarily mean that they are more accurate. The methods that we talked about in the last session are equally accurate in certain situations. But doing forecasting is really important to a lot of organizations, definitely in supply chain and a lot of other areas too. Forecasting is really where companies attempt to match their demand rates with their production rates. And this is especially important in retail organizations where they have to produce materials ahead of time, and they're doing that for what they're predicting to be a demand, especially if their products will spoil or go out of date at some point. And so I wanted to show you this video as we get started today about Nestle and how Nestle uses forecasting and the importance of Nestle's forecasting in doing their demand planning.
Nestle DSD is the largest company-owned direct store delivery system in the United States, supplying grocers with products like drumstick cones, DiGiorno pizza, and Häagen-Dazs ice cream. The challenge for demand planning is to make sure these products, and many more, make it to the right store at the right time. For many years, demand planners at Nestle were struggling with inaccurate forecasts.
As we were growing rapidly, we were getting into new and different channels with different products, and so our portfolio was expanding. Again, as I mentioned, the service expectations were increasing. And the cost reduction expectations were increasing. So it was, as a supply chain professional, all those start to oppose each other. Gosh, I want more and better service, but I want to do it with less cost and less inventory.
Nestle needed a robust solution that could help improve forecast accuracy.
We lacked the ability to see the level of detail we needed. We lacked the tools to be able to distinguish between a customer's demand versus a distributor's demand. We were trying to be surgical, but without the right tool set.
For a DSD company, it's very important to know specifically the product, the location, and the week that you need it. So for us to know that overall, the Dryers brand is going to sell X amount of units in a given month, it doesn't really help us out. It doesn't help us to get the product where we need it to be at the exact time we need it to be there.
We were solving a lot of our problems with inventory. We weren't horrible at forecasting, we just weren't as good as we knew we could be.
Nestle's demand planners understood that improved forecast accuracy could result in better customer service and reduced inventory costs. The team began searching for a technology partner, one that could offer a better solution for forecasting demand.
For us, it was about a really strong statistical engine, a really good set of robust user tools, a good set of reports, a good availability of data that we could quickly report on. And last but not least was a vendor that really supported our project.
Nestle found that partner in SAS and its demand-driven forecasting solution, including the powerful Demand Planner Workbench, which provided them with a highly flexible forecasting platform.
Demand Planner Workbench is a very flexible tool. It has the capability to let the demand planners to review forecast at a different dimension by different product category and by different customer level. And the demand planners will be able to make changes and adjustments based on the recent market intelligence and publish the results to other business partners across the entire organization.
With the Demand Planner Workbench, promotional activities at Nestle now have direct forecast impact and transparency, which leads to more accurate forecasts.
A significant portion of our volume is driven by promotion, and therefore the price points are changing, the displays, the promotional tactics are changing, and the ability to forecast that accurately is absolutely critical for a supply chain organization if we want to deliver on both service and cost.
So if I have a demand planner that says, I know that the drumstick cones are going to do much better next week or 2 weeks now or 3 months from now, and it's a national event. We're gonna advertise. That person can go in and touch Drumstick nationally. Or if they have a very specific region of a chain that's going to do a sampling program, or they're going to get a bunch of end caps that we didn't plan, I can touch it at that level too. So I've got the spectrum of being able to touch and affect that forecast. That's the flexibility of the workbench.
The sales and operation planning process has improved too, resulting in a sales force that is more involved and better informed.
You know, using SAS, we now have more information about what our customers are doing, what kind of lifts we're seeing because of the different promotions that we're running. And so now we're going to those S&OP meetings with that type of information. So instead of talking about how a brand is going to do next quarter, we're talking about a specific retailer, the prices and the promotions that they're running, and what kind of volume that we're seeing.
The results? Nestle says they are quite remarkable.
From a forecast accuracy improvement standpoint, versus the original baseline that we had, we made improvement between 3 and 5 points.
And every point of improvement is worth a lot of money from the full supply chain standpoint. It's not just about getting a better score. There are real dollars associated with that forecast accuracy improvement.
With this tremendous improvement to the bottom line, demand planners can focus on making sure that Nestle products are where they need to be, when they need to be there.
And you're able to see a much more robust picture of your data, a much more robust picture of your business that people can make better decisions on. Right? That's the return on information. It's being able to see all the nuances in your data, all the nuances in your business, and make better decisions. By having the right signal across all our products, all our channels, all our locations, means we get to accomplish our goal of right flavor, right time, right store. And that really is what drives a DSD business. It's about the service to that customer, right flavor, right time, right store.
So you can see there in that video that forecasting really is relevant for a lot of different companies. It really is important for maintaining the profit levels and operationally the success of real organizations. You can see there in that video too that in supply chain we are using technology, and in our classes in supply chain our professors are using some of the latest technology to be able to help us do some of those analytics, and so you definitely get to experience some of that in the supply chain major. The other thing that I really like about this video is that it highlights the connection between supply chain and the other areas of the business. So not only is this forecasting or this work that they're talking about doing in the video related to buying raw materials, producing those Nestle products, and then distributing those and getting those located where they need to go, which is the supply chain. That's certainly part of it. But it also is integrated in with sales and marketing. Sales, marketing, also finance, all of those different components of the business are collaborating together in creating this forecast and using this forecast to make the company run successfully. So today we're going to go through a few more forecasting methods. We're going to also talk about causality and correlation at the end of the class, just as a concept, and just so that you can recall only the calculations that we do in these videos, where you actually see me going through the calculations in the video, and then at the end of class there will be practice problems in the practice problems section of Blackboard. Only those calculations are on the exam. The textbook goes through many more different calculations. We are not covering those. For this section, there are a couple of principles, linear regression, multiple linear regression, and I want you to understand the principles, and we'll talk through that. Everything that I talk with you about in these slides and in this video is fair game for the exam, but as far as the calculations go, just what we do here in these videos. All right, so let's get started. All right, so this is just a reminder. This slide is copied over from the last video that you saw. It's just describing the various types of quantitative forecasting methods that we're covering in this class. Some of them more extensively than others. There's a few there you see there with asterisks where we are modifying them or we're just covering them conceptually, and so we're going to cover those today in class. This is not an exhaustive list of forecasting methods. There are a variety of them, but these are some of the most common ones that are used. There's no one forecasting method that's necessarily better than another one. They each have their strengths and weaknesses for different markets or different situations, but it's going to be important for us to measure the accuracy of each one of these methods. And when we, in our video for next session, we will be talking about how to calculate that accuracy, the accuracy of these different forecasting methods. So maybe let's start by doing a little bit of a review, and let's do it this way. Now, I don't know how many of you are familiar with fantasy sports. So let me explain how fantasy sports works a little bit and see if we can figure out how forecasting might be used with this. So with fantasy sports, what typically happens is you get together with a group of friends, and depending on what the sport is, it could be baseball, it could be football, whatever it happens to be, and each of you chooses players. The players don't have to be on the same team. They can be on different teams, but you choose players, and then based upon how that player performs in upcoming games or an upcoming week, then there's some sort of a score that's calculated, where you're competing against your friends. So whoever ends up with the best score based upon individual player performance sort of wins for that week. And you can, some people have fun sort of competing in this way, guessing at who is going to be a good performer in terms of a sport. So let's go through a few scenarios. Let's imagine that we're looking at football, okay? So we're looking at football, and let's look at a running back, somebody who runs the ball. And one of the stats that would be posted would be number of yards gained. So the number of yards that person ran. So let's say that you're trying to choose your fantasy player. One method that you might use is you might say, you know what, I'm going to look at last week, and I'm going to say, who was the runner who ran the most yards last week? Because if they ran the most yards last week, surely they're a good player, and they'll probably run a lot of yards this week. So if that is the method that you're using to choose your player, think about these methods. We've got these different quantitative forecasting methods here. Which forecasting method are you using? If you say, I'm going to look at last week's players, I'm going to find the one with the most yards, and I'm going to choose that player. The one with the most yards, I'm going to say will be the best player this week. What method of forecasting are you using? Well, sure, you're using the last period or the naive forecast. Okay, so what if you say, you know what, I want to look back at a few weeks. Let's look back at the last 3 games that people played. And what I'll do is I'll take the yardages from the last 3 games and I'll average them together. And then I'm going to pick the player that has the highest average yards for the past 3 games. Now what forecasting method are you using? Sure, you're using the moving average forecast. But there's another way you could do it. You could say, you know what, the most recent performance of a player is the most important. It's the one that's going to be most relevant to how that player is going to play this coming week. But I still want to include data from further back, because a good player will have good performance over a series of weeks. And so maybe you say, okay, I'm still going to look at the last 3 weeks, but what I want to do is I'm going to weight last week's performance by 40%, and the next week's I'm going to do the week before that. I'm going to weight it 30%, and the week before that I'll weight it 30% to find some sort of aggregate weight as kind of a weighted average. Well, then you'd be using the weighted moving average. Okay, so there's a variety of different quantitative forecasting methods that you could use to determine who are going to be the best players this coming week, and you never know. It's always someone different, and there's no way to really predict who will be the best players. The best that you can do is look at their past and try to make a determination of what that's going to play into for the future. Now look, with fantasy sports, you're just having fun. I don't know if it's just for bragging rights or if you actually have a little bit of money riding on it. But this is the same thing that real companies are doing. Real companies are essentially, they're betting on their performance. based upon a forecast. They're forecasting how many we're going to sell based upon what happened in the past, how many we need to make, how much material that we need to buy. And this plays into their overall performance. It plays into the profits of that company. So this is serious business. I mean, millions, billions of dollars based upon bets, essentially, that companies are making based upon forecasting methods. So if you were a company and you had millions of dollars riding on this decision you're making, you would want to choose the best model. You would want to choose the best forecasting method. And that's why we are going over so many different models, because there's a variety of these models that can be used in different situations. This is going to be useful in supply chain for forecasting demand, output of a manufacturing process, cost numbers. For sales, you're going to be forecasting sales numbers, forecasting what sort of sales you're going to have in the future, what the market's going to do. For accounting, you're going to need to be forecasting profit numbers. And so it doesn't matter, what your major is, you're going to be using these different forecasting methods. All right, well, so let's talk about some of these more advanced forecasting methods. All right, so first is the exponential smoothing model. So you see the formula here, and as a reminder, all of these formulas will be given to you on the exam. If you want to know what the formulas are going to look like on the exam, the exact formula in the format that it's going to be presented to you on the exam is printed in the exam review sheet. So if you pull up the exam review on Blackboard, you can take a look there and see on the back, you will see a selection of the different formulas, and those are the same screenshots that will be used on the exam. So that is there for you. So this is the exponential smoothing model. Let me talk you through this formula, but I think the easiest way to use it is really just to see an example and use it. So we're going to jump into that pretty quickly, but let me walk you through the formula here, the different variables that are included. So the first variable that you see there is f with the subscript t plus 1. So that is a forecast. Okay, that is a forecast for a time. When you see t plus 1, that is some time in the future. Okay, so that's our future forecast. A forecast for t plus 1. If t is in days, then this is the forecast for tomorrow. All right, t would be right now, and plus 1 is tomorrow. All right. So we're forecasting for what's going to happen tomorrow, or we're forecasting for what's going to happen next week, or what's going to happen next month. But that's our f t plus 1. Okay, so that equals some number alpha. So alpha is it's called a smoothing constant. It's just a number that's between 0 and 1. So it's going to be some decimal value between 0 and 1. And this variable in these questions on the exam, they will always be given to you. I'm just going to tell you what alpha is. I guess in a minute I'll tell you kind of where alpha comes from. But for all you'll have to know is that I'm just going to give you what alpha is. All right. So alpha is a smoothing constant that gets multiplied by the demand. D sub t, that capital D sub t, that is the demand that is happening right now. So if we're talking about days, that is the demand today. Or if it's in terms of weeks, that is the demand this week. So I'm forecasting for next week, and I'm looking at my demand for this week to help me make that decision about what the forecast is for next week. And so I take the demand, I multiply it by alpha. Then I add to it 1 minus alpha. So this is just 1 minus alpha. So if alpha is 0.3, then 1 minus alpha is 0.7. If alpha is 0.6, then 1 minus alpha is 0.4. So I'm going to take that number, 1 minus alpha, I'm going to multiply it by f sub t. F sub t is what I had forecast for today or for this week. So sometime in the past, I had predicted what the future was going to bring, and I had predicted a forecast for this week, and that is f sub t. Now, once I get into this week, I see what the actual demand is. That's d sub t, and I'm going to use those two numbers to determine my overall forecast. All right, and we'll talk more about this. But here, this is kind of a neat thing. This alpha value is we are not deciding what that is for this class, but in our supply chain management classes, our supply chain management majors have the ability to adjust that alpha value. And adjusting the alpha value gives you an opportunity to put more weight either on what actually happened, that's the demand, or on what you thought was going to happen, the forecast. Okay? So yep, let's see some more examples. So remember, a forecast will always be wrong. So in this example, you can see in that little graph that we have a forecast there of 100. We thought that the demand was going to be 100, but then we get into that time period, that week or that month or that day, and we realize that the actual demand is 110. So we thought it was going to be 100. It was actually 110. And now the next thing that we're doing with this exponential smoothing forecast is we are trying to predict, well, okay, so what's the next period going to look like? So if we're talking about weeks, we thought that the demand was going to be 100 this week. The actual demand was 110 this week. And so we're saying, okay, well, we thought it was going to be 100, but it was actually 110. So what will it be next week? And we get to choose how much, and you might say, well, it's going to be somewhere in between 100 and 110, somewhere in between there. Well, we get to choose how much weight we put on the demand and how much weight we put on that forecast. And that's how we use that alpha value. Now, just to remind you, on the exam, you will not have to choose alpha because I'm just going to give it to you. Okay, so you can see that if alpha is 0.1, then we put most of the weight on our previous forecast. And so, the forecast would be 101. If our alpha value is 1, then we place all of the weight on the demand and none on the previous forecast. So an alpha value of 1 is just the same thing as the naive forecast. It's saying the future, whatever next week or next month is just going to be exactly what the real demand was this week. Okay, now this exponential smoothing formula has a forecast value in it. So you can imagine that forecast value was based upon our forecast from last week. Okay, and so when we go back to last week, that forecasting value was based upon the week before that, and that forecasting value was based upon the week before that. So one of the neat things about exponential smoothing is that it doesn't require a whole lot of data, but it embedded in that formula is all of the previous forecasts. You can also see that you can't start forecasting with exponential smoothing. You have to have some way of creating that initial forecast. So, and that'll be something that's given to you. It says, hey, we've started out with this particular forecast and then work forward then with this exponential smoothing formula. So here are some features of exponential smoothing. So exponential smoothing, the formula itself incorporates all the previous forecasts that you've had, but the way that it works, it puts greater weight on the more recent data, which is a reasonable assumption to make in a forecasting model. It also just requires very little stored data because all you need is the previous forecast and whatever the current demand is. Then we can adjust the alpha value depending on what we want the forecast to give us. So if we're looking for stability, if we're looking for a forecast that is more stable, that will not change very much when the actual demand data changes, then we'll use an alpha value that is low. So a low alpha value puts more of the weight on the previous forecast, less of the weight on the actual data, so you can end up with a more stable forecast. If you're looking for more responsiveness, so you're looking for your forecast to respond very quickly to changes in the demand, then we'll use a high alpha value. And the high alpha value then will put more of the weight on the current demand, less weight on the previous forecast, and then you'll have a more responsive forecasting model. But as a reminder, you do not have to choose alpha. We will always give you alpha on the exams. But in the supply chain, in our supply chain curriculum, our majors do learn how to change and adjust that alpha value and actually choose it. The smoothing constant, it says here, is typically somewhere between 0.05 and 0.3. That is not a rule. It's just that's a typical range of values that are used for that smoothing constant, but they can certainly be outside of that. All right, so let's look at this first example using exponential smoothing. So imagine that you are part of the leadership of a student organization and you're planning an alumni meeting for the next year. Now you've got attendance, you have historic attendance at this particular meeting, and you're trying to make a prediction about what the attendance will be this upcoming year. You're trying to make the plans for that. And you don't know what exactly the demand is going to be. The only thing you know is what the demand has been historically. Now, in this example, again, this is very similar to what you'll see on an exam. I'm just going to give you an exponential smoothing constant. I'm going to tell you that that constant is alpha. And I'm going to tell you that the forecast, in this case for the year 2014, was 175. Okay, so, and then you have the formula there. So let's walk through this. Now, the secret to doing exponential smoothing is to understand what year you're standing in. Okay, to understand what year you're standing in. And you have to imagine with exponential smoothing that you're in a particular year, you're looking forward to the next year, but and you don't know any of the future data that's there. Okay, so let's take a look. So to get started, all we have is we have the demand for 2014 and we have the forecast for 2014. Now, so where did that 175 come from? Well, that 175, of course, it's given to us in the problem. But what happened was before 2014, so in 2013 sometime, for instance, there was someone that did some math and created a forecast using some method, and they had predicted that in 2014 that 175 people would show up at this alumni meeting. But you know what happened? 175 people did not show up. 180 people showed up. So we had more demand than we had forecast. So now what you have to do is you have to imagine that you're standing in 2014. So standing in 2014, you know that the previous forecast was 175. You know that someone had predicted the demand was going to be 175. And you know you just got out of the meeting, and you know that 180 people actually showed up. And now what you're doing is you're trying to make a prediction about, well, what's going to happen next year? Okay, now I know that on this slide and in these problems, it says what happens next year. So it says that in 2015, that 168 people are going to show up. But if you're standing in 2014, you don't know that. Okay, so you have to imagine, I'm standing in 2014. I'm going to try to predict what the demand is going to be in 2015, and I don't know what the demand is going to be in 2015. Okay, so imagine you're standing there in 2014. You only know two pieces of data, two pieces of information. You only know that the current demand is 180, and you know that someone previously had forecast that it was going to be 175. Now look, if we look at the forecasting formula using exponential smoothing, we have all the numbers that we need there. Okay, so f t plus 1, the forecast for the next period, the forecast for 2015, okay, because we're standing in 2014, so the time currently is 2014. We're forecasting into 2015, so the forecast for 2015 equals alpha. Do we know alpha? Sure we do. Alpha is 0.1. It's just given to us in the problem. Multiplied by the demand that we're seeing right now. What's the demand in 2014? 180. Okay, so we take 0.1 times 180 plus 1 minus alpha. What's 1 minus alpha? It's 0.9 multiplied by that forecast that we had for 2014. So that's 175. Someone previously had forecasted into 2014, had forecasted it was going to be 175. That's the f sub t that you see up there in that formula. So all we have to do is to do that math. Just write out that equation and calculate it out. All right, so the forecast for 2015 is 0.1 times 180 plus 0.9 times 175, which equals, well, 0.1 times 180 is 18, 0.9 times 175 is 157.5. So we add those two numbers together. Now our forecast is 175.5. So when we're standing in 2014, when the year is 2014, I'm looking forward into 2015 and I'm saying, how many people do I think are going to show up at this event, at this alumni meeting? And what I think is going to happen is that 175.5 people are going to show up. But is that how many people showed up? No, it's not. 168 people showed up. Okay, so now I'm standing in 2015. And again, I only have two pieces of information, two pieces of data. I have the current demand, which is 168, and I have the forecast that I had made previously, that 175.5. I thought 175.5 were going to show up, but actually 168 people showed up, and those are the only two pieces of information that I'll need, including alpha, to be able to forecast what I think is going to happen in 2016. So this is going to be kind of a trick question for you, okay? How many people are going to show up at the event in 2016? And the answer is, I don't know. Now, I know it's written down on this slide, but you don't know. If you're standing in 2015, you don't know how many people are going to show up in 2016. So when you do the forecast, the only information that you have is the demand that you're seeing right now and whatever you had previously forecast. And again, you just plug these into the formula. Alpha is 0.1. The demand that we are seeing currently is 168. 1 minus alpha is 0.9. And the forecast that we had created was 175.5. Plug those numbers in, and here's what you get. All right, so we are predicting that 174.75 people are going to show up at the event in 2016. But that's not what happens. 159 people show up at the event in 2016. Okay, so here's what I'm going to do. I'm going to pause here. You're going to follow this pattern through until you get all the way to 2019. Okay, so I want you to take a break. I want you to pause the video, and I want you to actually try to do this. And then I'll show you on the video, I'll show you the answers to these, and we can walk through them slowly together to make sure that you understand how to do this. Now, one thing I'll remind you of, you might be curious about this, especially since we see some decimal point values in here. On an exam, if you will just use 4 decimal places in your calculations, then you will get the same answers that I get on the exams. Okay, so just use 4 decimal places. These are rounded here to 2 decimal places, but if you use out to 4 decimal places, then you won't have as many rounding errors, and you should be able to find the same answers as I do on an exam. All right, pause the video now and give yourself a chance to walk through these last few forecasts. See if you get the same numbers that I get. All right, so for the next one, we are standing in 2016, and we only have 2 numbers. We have that the current demand really is 159, and we have that we had predicted that the demand was going to be 174.75. So we put those 2 numbers into the exponential smoothing formula, and we get 173.175 as our prediction. Okay, now you're standing in 2017, and you only have 2 pieces of information again. You have that you had predicted there would be 173.175 people, and you know that you actually see 175 people. So you take those 2 pieces of information, the actual demand and your forecast, 173.175, and the actual demand, 175, and you plug those in to the exponential smoothing formula, and this is what you get. All right, you get 173.3575. Okay, so now finally, we're in 2018. And this is really where we, in this example, this is really where you stand. You stand in 2018 and you're looking into 2019 and you're trying to say, well, how many people are going to show up in the next year? And you have no idea. but you only have two pieces of information. You've got the actual demand, 190, and you have what you predicted the demand would be, which was 173.3575. Okay, well, so let's plug this in to the exponential smoothing formula and see what we get. All right, so we're going to predict 175.02175 people will show up in 2019. And how many people actually will show up at the event in 2019? Yeah, the answer is we have no idea. We don't know. I mean, the best guess that we have right now with exponential smoothing is 175.02175. But keep in mind, this is not our only forecast. So let's do this a couple of different ways, all right? So what if I had said the naive forecast? What's the naive forecast for 2019? You figure that out, the naive forecast. Okay, so there we're standing in 2018, looking into 2019. We see that the demand is 190. And so naive forecast just says, okay, let's guess that there'll be 190 people that show up next year too. All right, that's the naive forecast. What if I said use n equals 2? Okay, n equals 2 moving average forecast. N equals 2 moving average, or a 2-period moving average. Okay, well, we're standing in 2018. I know that 190 people showed up this year. I know that 175 showed up last year. So moving average just says take the average of those. So 175 plus 190, which is 365, divided by 2, which is 182.5. All right, let's do another one. What if I said use a moving average forecast using 4 periods, a 4-period moving average? Well, you could do that. 4-period moving average just takes the last 4 data points and averages them. So 190 plus 175 plus 159 plus 168, and then divide that by 4, and you get 173. Now let's do another one. What if I said use a weighted moving average forecast of 0.6, 0.2, and 0.2, weighted moving average? Okay, so first, is that a valid moving average? Is that a valid weighting for a moving average? Well, let's see, 0.6, 0.2, and 0.2. 0.6 plus 0.2 plus 0.2 equals 1. So yes, it is a valid weighted moving average. And so then we can do that. When you see these numbers 0.6, 0.2, 0.2, what you do is you take the first number that you see, you apply it to the most recent data point that you have, then you apply the next number to the next most recent, and so forth. So in this case, you would take 0.6 multiplied by 190, and then you would take 0.2 times 175 and 0.2 times 159. You add all those together and you would get 180.8. So now we've got several different forecasts, and I don't know if you wrote all these down, but we have several different ones. We've got 190, we have 182, 173, 180.8, and here we've got 175.02. We've got all these forecasts, and what's the right answer? Okay, so on an exam, I'm going to ask you, I'm going to say, give me the exponential smoothing forecast for 2019, and then you would do it just like this slide. Or I would say, what is the naive forecast for 2019? And you would say it's 190. Or I will say, what is the 4-period moving average forecast for 2019? And you would add together those 4 most recent data points, divide them by 4, and you get 173, and that would be the answer. Okay, those are the answers. That's how you get the answers there on the exam. Let's talk about real supply chain management for a minute, though. Okay, so real-world supply chain management. You're on this, the leadership of this organization, and you're planning for the next year, and you've created this forecast. How many people would you plan for the next year? How many people would you plan for? You created the forecast. Okay, well, you could plan for 175. You could plan for 190. That would be using the naive forecast. You could, just pick one of these forecasts and plan for that number of people. But this is one thing that I like about supply chain management, and that is that supply chain management is not what are all the numbers, how do I do the math, then give me the output of the numbers, and then that's just the answer and you just follow the numbers. Supply chain management involves thinking about creative ways of configuring situations using the data that we have. So, I might say, okay, I'm going to plan for, as a supply chain manager, you might say, I'm going to plan for 200 people to show up at this event. And the reason I'm going to plan for 200 is that it's an alumni meeting. They're going to be donating money. I want to make sure that I have plenty of food. I don't want anyone, I don't want anyone to go away hungry, not have enough food. So I'm going to plan to have more food than I think that I'll need to make sure that everyone is served. Okay, so that's one strategy that you might use. Now, I might say, you know what I'm going to do? I'm going to plan for 168 people. And you might say, well, that's crazy. Why would you plan for less people than you're forecasting to actually show up at the event? Well, we're a student organization and we're short on cash. We can't afford to have a lot of extra food and that goes to waste. We want to make sure that it's all used. So maybe what happens is I say, you know what, I'm going to talk to all of the officers of our student organization and I'm going to tell them all, hey, look, we're going to show up at the event. We're going to buy enough food for 168 people. Then we're going to show up at the event. If more people show up than 168, then what we'll do is we won't eat. We, the officers, will make sure that we have enough in place so that everyone can get fed. Okay, so that might be something that we decide to do. There are a variety of different strategies then that we can use. We're going to use the math for guidance, but then we're going to use our intellect and our creativity to come up with a solution for figuring out how can we actually make this happen. All right, so in these graphs, the black line represents the actual data, and the smaller lines, those the lines in color, those represent different exponential smoothing forecasts with a variety of different alpha values. You'll notice here that when the alpha value is higher, the higher the alpha value, the more responsive it is to changes in the data. So it follows the data more closely. You'll notice that an alpha value that is smaller, like 0.1, it's a little more smooth and it doesn't react as quickly to changes in the data. You'll also notice another feature of this exponential smoothing forecast is that it's always lagging behind. So the actual data is moving along, and then it takes a period or two for the exponential smoothing to react to those changes in the data. So exponential smoothing is not well suited for forecasting trends, like you see there in the graph on the left, or seasonality, which is what you see in the graph on the right, because they tend to lag. So it's most used in flat data, data that is trending slowly or changing slowly, or data that is level. All right, so these are some additional advanced methods for dealing with forecasting. Now, we are going to go through some very basic linear regression. I'm just going to show you how to use a linear regression formula, but I just want you to know that these different forecasting methods exist, and in general, what they're used for. And so all you'll need to know, I'm going to explain right now. Now in the textbook, they go into a lot more detail. There are a lot of practice problems or examples of these in the textbook. You will not be calculating these on the exam, so you don't need to worry about those sections of the textbook for calculations, just what I'm going to be showing you here in the video. So first is adjusted exponential smoothing. Just like most things in supply chain management, we have calculations, and the calculations are really based upon some pretty simple formulas. And what we do is once we get good at using a particular formula, then we can add some small complexities to that formula to make it more useful. This is one example. So there's a thing called adjusted exponential smoothing. You will not need to use this method for this class on our exams, but it also has an alpha component, very similar to the one that we just used, but it contains a trend adjustment, which is a beta value. And so all this is, it's exactly the same formula. We just add in one additional component, into that formula, and then that's how we use it. So the only thing you need to know is that adjusted exponential smoothing can be used to adjust for trends. All right, we have linear regression forecasts. A linear regression attempts to model a trend using a straight line. You may have done this calculation in a statistics class. I'll tell you that in supply chain, now for this class we are not calculating a linear regression, but in supply chain management we just use Excel, because in Excel it's really easy to do a linear regression. There's just a couple of different commands, a couple of little buttons to push in Excel, and we can have Excel create that linear regression formula for us, and so that's what we tend to use. And so we'll look more at this in the next slide so you can see what one of those looks like, and I'm just going to have you be able to calculate using the formula. Okay, so next is a seasonally adjusted linear regression. And all this does is it takes that linear regression and it just makes adjustments to it based upon whatever season of the year that we're in. So as demand naturally fluctuates up and down, the seasonally adjusted linear regression has factors that are multiplied in to give your forecast that seasonal lift or a seasonal fall, and so that's what those are used for. In supply chain management, we typically use software to help us out in calculating these sorts of forecasts. All right, so let's use a linear regression forecast. So as a reminder, you do not have to calculate this forecast. So see in the graph here on this slide, see how there's a formula there that says y equals 748.33 plus 119.38x, and that's the formula there for that red line in the graph. That formula, you can calculate it, but in supply chain, we will use Excel typically to calculate a linear regression forecast similar to that. So I am not requiring you to be able to calculate that forecast. I just want you to be able to use the formula. So that's what I want to do on this slide, is teach you how to use the formula. So a linear regression forecast it just puts the forecast in an equation that looks like a line. Now, I don't know if you remember this from your high school algebra class, but the formula for a line is y equals mx plus b, where m, which is multiplied by x, is the slope, and b is the y-intercept. And this is exactly the same as this formula. You can see here, this formula, you look at the formula that's there on the graph, it is in the form y equals b plus mx, essentially, but it's y equals mx plus b. It's the same type of formula. It's an equation of a line. So the way that this formula works is y, in this case, is the demand. And that's the predicted demand, and the predicted demand is a function of time. And so along the x-axis there, along the bottom of this graph, you'll see periods. So it might be days, it might be weeks. Let's call it weeks. So you see week 10, week 11, week 12. There's actual data that occurs there, but the red line is the forecasted value for that particular week. So with this type of a formula, let's do this. It says, what is the forecast for period 16? So let's do that. So at week 16, we're going to forecast what the demand is going to be. We do that using the formula. All we have to do is plug in the number 16 for x. So you take 748.33 plus 119.38 multiplied by 16, and then we get, looks like something a little over 2658. Okay, so 2658, that is a number on that red line, at week 16. Now, one of the neat things about this linear regression forecast is we can forecast any number of periods into the future. So for example, we can say, well, what is the predicted forecast at period 37? And you can see period 37 is way in advance. It's way in the future. I don't know how many weeks, several weeks beyond what the data is we currently have. But we can still forecast that far out. All we do is take 37 and plug it in for x, and then we can calculate y. So here's how that calculation would look. So here is our forecast for period 37. You can see that there. All right, so on an exam for linear regression forecasting, I just want you to be able to use the formula. I will give you the formula, and I will say, give me the forecast for period so-and-so or for time period so-and-so, and then you're just going to plug in that number into the formula to give me the forecast. Now, the only other question that I may ask on a linear regression forecast, well, here, I'll ask it here on this one, and that is, you can see that this is an upward slope. You can see that the demand over time is increasing. So I might ask you a question like, what is the expected growth that happens every period? What's the expected growth in terms of demand every week here? Or I may ask it a different way. I may ask, on average, how much does the demand increase every week? Okay, that's asking the same question. And you should be able to look at the formula to determine that. But we could do this. We can do this using some math if you'd like. We could calculate. You can calculate. Well, you can try this. Calculate the demand for week 10. So that's putting in a 10 for x. And then calculate the demand for week 11. So week 10, week 11. So for week 11, just plug an 11 in for x in the formula. How much different are they? That's really what we're asking. And when you do that, you will find the answer is 119.38. So every period, this linear regression forecast, it predicts that every period, in this case every week, if these are weeks, every week, my demand is going to go up 119.38. Sometimes a little more, sometimes a little less, but on average, it's going to go up 119.38. So that's another question that you may be asked on an exam. All right, then we have some causal forecasting models. These are also known as correlation models. There's a pretty extensive section of the textbook that goes over these causal or correlation models. As a reminder to you, you will not need to calculate these. I know in the textbook they go through all the calculations. You do not need to go through these calculations for the exam. I'm going to tell you everything you need to know about this topic right now, and it has to do with these definitions. So these correlation models, these causal forecasting models, what they do is they try to look at certain variables and make predictions on the future based upon variables that we're seeing. So there's a couple of types. One is linear regression. That's where you look at one variable and you are trying to predict one other variable. Then there's multiple regression, and that's where you look at multiple variables and you're trying to use those multiple variables to predict one variable sometime in the future. And so you need to understand the difference between a dependent variable and an independent variable in these types of models. So this is kind of how I remember these, and I don't know if this is going to help you or not. You can see the definition here on the slide. There is an independent variable. That is the variable that is assumed to do what we refer to as the causing. That's why it's called a causal forecasting model. I kind of refer to that. That's the variable that we are that we can control. It's a variable that we can control, or it's a variable that is just going to be happening. And it is the one that is doing the influencing. Okay, now the variable that is being influenced is the dependent variable. That is, it says here in the definition, the variable that is assumed to be caused. I kind of think of it as it's the variable that depends on something else. It's the dependent variable. It depends on the independent variable. So when the independent variable happens, then the dependent variable will change. So when the independent variable or independent variables go up, then the dependent variable will either go up or down in response to that. The dependent variable is the variable that responds. Okay, so here are a couple of examples. The first one is a linear regression because I'm only talking about two variables here. It says the money spent on drought relief is mathematically related to rainfall levels. What that means is that as it rains either more or less, that is going to influence how much money we will spend on drought relief. So, if it rains less, if we get less rain, then we'll spend more money on drought relief. And if it rains more, we will spend less money on drought relief. So in this example, rainfall level is the independent variable. It is doing the causing, and the drought relief, the money that we spend on drought relief, that is the dependent variable. That's the one that's being caused. Notice that it doesn't work the other way around. In other words, I can't spend less money on drought relief in order to make it rain more. The rain is doing the causing here in this example. So the rain in this example is the independent variable. Now, same thing, next example is a multiple regression equation or a multiple regression example. If you're having a party, you're going to want to try to predict how much food is going to be consumed. So the amount of food that is consumed is the dependent variable. And that dependent variable, the amount of food that is consumed, is going to depend on a ton of different things. It's going to depend on how many people are at the party, when they ate last, how many food stations are available, the taste of the food, the presentation of the food. There's lots of different variables that play into that. And we could actually create a mathematical equation that would take all of those independent variables, how many people show up, when they last ate, all of those things, and mathematically relate that to that dependent variable, which is how much food is going to be consumed at that party. Okay, now one of the dangers of this is, mathematical equations. You can actually fit correlational models, correlational equations. You can fit these to any set of data. And so one of the risks is that there are people that will take different variables, they will put them against one another, and then they will correlate them. They will find a correlation variable. I'm not going to go into the details about what that means. And then they will say that this proves that one variable causes another, or this proves that if I want one variable to change, then I need to change this other variable. It actually takes quite a lot of work to prove that one variable causes another one to happen. And so I want to encourage you that just because something is correlated, and I know that these are called in the textbook causal forecasting models, but just because there are variables that correlate with one another does not mean that one variable causes the other one to happen. That's an entirely different thing. So I want you to see this short video that's going to explain a little bit about why that is and how that is.
Welcome. I came here today to warn you about the dangers of ice cream. You may not be aware of this, but these innocent-looking cones are one of the major causes of drownings. If you plot a graph of the number of ice creams that are sold and you compare it with the number of drownings, you can see there is clearly an upward trend. And I think it's very safe to conclude from this that we should ban ice cream because it's very dangerous. What's really happening here is, of course, that there is an underlying factor, which is nice weather. And if the weather is nice, more people will go out swimming and unfortunately drown. And at the same time, more people will buy ice cream. And it's not the ice cream that's causing the drownings. Jumping to an incorrect conclusion about causality when you see a correlation is the most often made logical mistake. And today my goal is to make sure that in the future you can recognize this mistake. The fact is that married men live longer than single men. If you look at the statistics, you see that this is really happening. And women's magazines, they like to conclude from this that marriage is very healthy for men because it makes them live longer. Well, a friend of mine, he likes to joke that marriage mainly makes life seem longer, but there is a causal relation. But it's the other way around. The fact is that men who are healthy and rich and well educated and have a much higher life expectancy, these are the men that are much more likely to find a wife. And the guys who have a very low life expectancy, so they're unhealthy and poor, they are not as likely to get married. So it's the high life expectancy that is causing the marriage, not the other way around. Let's move on to a more serious example. There was a study in 1999 that showed that young kids who sleep with the lights on, that they have a much higher probability of becoming short-sighted later in life. And in the popular media, this became that bed lamps were night abuse, children's abuse, and that it was very bad if parents used lamps in the bedroom. And many parents were worried. But luckily, the article had to be corrected the next week. Short-sightedness is genetic. And so it's parents who are short-sighted, and those are the parents who like to leave the light on in the bedroom. And they also are the parents who have short-sighted kids. So the next time someone wants to prove that there is a causal relation between something and something else, and if they point out to you that there is a very strong relation, remember that it's not enough to have a correlation. You need to know why it does and how it does. So when in doubt, just remember the ice cream. Thank you very much.
So if you're curious to learn more about supply chain management or interested in becoming a supply chain management major, I'm really going to encourage you to start participating with, perhaps even joining our student organization, SPO. You do not have to be a supply chain management major to start getting involved, because SPO has lots of different activities and events that are open to all majors. SPO is very active. They have a lot of interactions with businesses, whether you're going to site visits or whether they're bringing in executives, hiring executives in for information meetings, for networking events. They have career mixers and mock interviews that are specifically tailored to supply chain management, so that you can really learn how to tailor your resume and your interviewing skills for a supply chain management interview. They have lots of different dinner meetings, networking events, as well as a variety of different social events that I think you'll really enjoy. So what this will do for you is it will give you exposure to our supply chain management students. These are going to be the professionals that are your colleagues in a supply chain management career. It will also give you exposure to real executives and real businesses that are actually practicing the things that we are teaching in the classroom. So it'll give you a really good exposure to what real supply chain management is all about. Make sure you visit them at bauerspo.org.